everyone. In this video, we are going to looking at reaction mechanisms. So the reaction mechanism is a sequence of reaction steps that describes the pathway from reactants to products. So remember previously we looked at the reaction potential diagram. We plot energy, the progression of the reaction, and we were saying that, okay, to go from reactants to products, we have to go through certain steps. And this reaction mechanism is looking at the steps in sequence as to how we go from reactants to products. So this reaction mechanism, oftentimes we will have to propose one, and then we do experiment on it to make sure it's right. So for a plausible reaction mechanism, it has to fulfill two criteria. First, the elementary steps must be summed up to give the overall reaction. And it must be consistent with the experimental rate law for the overall reaction. So it's just like the way how we can figure out the plausible reaction mechanism is just like the scientific method. We determine the rate law, and then we propose a mechanism. We use it to predict how it should work, and then we keep testing it until it works. Then we can say that, okay, this is the right one. So let's look at what overall reaction and elementary steps mean. So overall reaction is the reaction stoichiometry. This is a balanced equation that we usually see. It tells you who the reactant is and who the product is, but it doesn't tell you where they came about. The elementary steps, it tells you which steps they take. So they basically break it down, tell you how it came about, and as an individual molecular event. So you can see that this reaction has two steps that it has to take in order to make it happen. So over here, this is illustrating how this is a molecular event. So right now we can see that, well, we have NO2 and NO2 reacting together. Only one molecule was exchanged at a time. One molecule was exchanged at a time. This is going to be enough information for us. The reaction mechanism is a very complex idea, and then we are going to talk about it this way for the purpose of this class. But if you're interested, you're more than welcome to dig into more about this. So remember, the first criteria for having a plausible mechanism is that the elementary steps must sum up to be the overall reaction. So this means that when we have step 1 and step 2, and this is the reaction mechanism. So we are trying to find the individual steps because this is what we can observe, right? In the reaction, we can identify the products and the reactants. But then the idea of proposing a reaction mechanism is how they go from reactants to products. So this is what we are trying to look for. So whatever you propose for the reaction mechanism, the elementary steps need to add up. So you can see we add up all the reactants and all the products. And then after we clean it up, it needs to equal to the overall reaction. And the things we crossed out that are the same before and after are called intermediates. These intermediates are species that are formed, but then they are consumed right after. So if you look into the elementary steps, well, after the first two reaction, we formed an NO3. But then at the next step, NO3 is immediately used up to form something else. So NO3 in this case is a intermediate because it's used up right after. And the way how we can identify them is literally adding up the first two steps. Whoever is the same before and after, so NO2 is the same before and after, we cross it out. NO3 is the same before and after, we cross it out. So those two are the intermediates because they are not in the final one. That means that they must be consumed during the reaction. And lastly, the idea is the rate determined step. So this is the slow step of the reaction. And the reason why it is considered rate determined is because the overall reaction cannot be faster than the slowest elementary step. That's why it's called the rate determined step. So now let's try to evaluate whether the mechanism proposed is a plausible mechanism. So remember, the first criteria is that the elementary steps must sum up to give the overall reaction. So in this case, if this is the proposed reaction, they have to add up to be this one. This one is usually easier to check. The second criteria is saying that we have the mechanism must be consistent with the experimental rate law for the overall reaction. So this is the part that we are going to be focusing on more because that part can be a little bit more confusing. So let's look at the first case. The first case is when we have a multi-step reaction with an initial slow step. So in this reaction, well, we can see that first of all, the first criteria is already checked because, well, the elementary steps do add up to the overall one. The second one is we have to check the experimental rate law and then the rate law of the proposed mechanism. So let's look at the predicted rate law based on this mechanism. So first thing is we have the rate determined step as the first step. This means that our overall reaction is going to depend on the first step because the first step is the rate determined step, and that also means that the intermediate is being reacted as soon as it is formed. So this is the rate determined step, and this is what we are going to be focusing on. So with that, we can write the rate law based on the mechanism, right? The rate law we can see is the rate is equal. Remember how we wrote the rate law? Is the rate constant multiplied by the concentration of the reactants. We don't care about the products. So it's going to be the concentration of NO2 and another NO2 because there are two. And then this is going to be K1 multiplied by the concentration of NO2 squared. And then we can look at the experimental rate law. This one is determined by the experiment. So over here, we are going to just give it to you. This is the rate. And you can see that in this case, we have KEXP because this is the rate constant from the experiment. Compared to these two, this is the rate constant that is from the proposed mechanism. We assign it and it's arbitrary. So remember, these two are arbitrary. The KEXP is from the experiment. So then we have the one from the mechanism. We have the one from the experiment. Now let's compare them. So these two have to be consistent with each other. And, well, because they have the same form, so both of them have a K to the NO2 squared. That means that they are consistent with each other. And since they are consistent with each other, this is a plausible mechanism. And we can also conclude from here that the rate constant we measured in the experiment is equal to K1, the rate constant of the rate determined step in the mechanism. The second case is when we have a multi-step reaction with an initial fast step. So what this means is that, well, over here is the proposed mechanism. And again, the first criteria to make sure it's plausible is making sure the elementary steps adds up to be the overall one. And it does. And then the second step is then to make sure that the rate laws are consistent with each other. So looking at this, we can see that in this case, we have a first step that is fast and it is reversible. So right now over here, you can see that we have a K1 that is the rate constant going from left to right. We have a K-1 that is a rate constant for going from right to left. This is the reversible reaction. We have a K2 that is describing the second elementary step from left to right and K3 for it. So remember, all these K's in the mechanism, they are arbitrary. We propose them. You can name them K, A, B, C, doesn't matter, as long as each of them have one. And then the KEXP is the experimental one. So now let's try to look at how we can isolate the rate law from this information. So now let's try to predict the rate law. So first, we're going to predict the rate law based on the rate determined step over here. So again, we're going to write the rate law as rate equals to the reactants, and then the rate constant. So K2, because this is K2, the second one, multiplied by the concentration of N2O2, and then the concentration of H2. So this is the rate determined step, rate law. However, based on this rate determined step, there is one thing that we can notice. So over here, based on this, we know that the intermediates of this reaction, so these are the ones that is in the product and being used up immediately. The intermediates include N2O2. Another intermediate is N2O. So these two species are inside the elementary steps, but are not in the overall. So one way to determine it is to track the reactants and products. The other way to do it is just add all these together, and cross out whoever is the same before and after. Whoever is the same is the intermediate. So you can see that this rate law has an intermediate in here. However, because they're intermediates, once they're produced, they're being used up very fast. So we can hardly get a measurable concentration of the intermediates. That means that our rate law cannot include a term that has the concentration of the intermediate. So every time we see a rate law that has a concentration of intermediate, we need to find a way around it because this concentration cannot be measured by experiment. So in order to do that, well, we can isolate the fast reversible step. So let's look at the reaction going from left to right. We can write the rate of the forward reaction is going to equal to K1, that's going from left to right, multiplied by the concentration of NO. And then it is going to have the second power because of the coefficient. So you can imagine this is NO plus NO. So our rate will be NO times NO equals to NO squared. And then the rate of the backward reaction, so remember this is reversible, is going to be the rate of the backward is going to equal to K negative 1 multiplied by this time the reactants are N2O2. So N2O2. So these are the two expressions from the reversible step. Now we can plug this into the we can write this in terms of the intermediate. So let's write this in terms of the intermediate, and then we can see that, well, the intermediate is N2O2, right? So this is the intermediate. So then for a reversible reaction, we know that the rate going forward is equal to the rate going backwards. This is just something by definition, backwards. So from this, we know that, well, this whole thing equals to that. So K1 NO squared is equal to K inverse 1 N2O2. And we are going to express this in terms of the intermediate. So N2O2 by itself is equal to, well, divides both sides by K negative 1 is K1 squared over K negative 1. And now we are going to remember this and bring it down to the next step. So now the next step is to plug our intermediate concentration expression that we got from the previous step, which looks like this, K negative 1, into the rate law that we determined from the rate determined step previously. So previously from there we say it's K2 times N2O2 and then H2. And then remember we said that, well, this concentration is an intermediate, we cannot measure it. So we went to the first step to rewrite it. Now we can replace it. So now we can say that this is equal to K2 times K1 over K negative 1 times NO squared times H2. And now we can see that both of these species are not intermediates. That means that their concentration can be measurable. So with that, let's compare our predicted one to our experimental one. So let me, again, write down the predicted one more time. So predicted. And this is going to look a little bit complicated. But then we predicted that it is K2 times K1 over K negative 1 times NO concentration squared times H2. And comparing these two, the predicted one from the mechanism and the one we got from the experiment, we can again see these two have the same form. They have a second order on NO and also a first order on H2. So they're consistent with each other. That also means that this chunk and the K experiment are the same thing because they equal to each other. So those two are the same. So we can say that the K experiment, so the rate constant we got from the experiment is equal to K2, so the second one, multiplied by K1, this one, divided by K negative 1. And that is how we can express the experimental rate constant with the rate constants from the mechanism and showing that it is consistent with each other. So with all that idea in mind, we are again going to look at some examples. So over here we have two examples whose reaction is a little bit less complicated. I will say less complicated. And hopefully this can help you refresh your memory. And again, if you feel comfortable, please feel free to pause the video and try it yourself. The first step of a proposed multi-step mechanism is as such. Derive the equation relating atomic fluorine concentration to molecular fluorine concentration. Atomic fluorine is this one because remember fluorine exists diatomically. Molecular is that one. So then this one, it is asking us to relate the two. So we will set the rate constant for the forward to be K1 and the rate constant for the backward to be K negative 1. So to express the rate, it is going to equal to fluorine K1. So K1 multiplied by the concentration of atomic fluorine to the first power, because remember, if it's not shown, the coefficient is 1, is equal to K2, sorry, not K2, K negative 1 multiplied by the concentration of the molecular fluorine to the second power, because it has a 2 as its coefficient. So this part, K1, that's K1, and that's K2. So it is asking us to relate them. So theoretically, this should work. This is the equation that is relating them. And if we want to be even more specific about what it is asking, expressing it in terms of, sorry, I just realized I made a mistake at the beginning. Atomic fluorine should be this one, and molecular fluorine is the other one. It's the other way around. Atoms are by themselves, and molecules are the diatomic molecule. I don't know how I mixed that up at the beginning. So the atomic fluorine, and all we have to do is to divide both sides by K to the negative 1 and take the square root. So that is K1 times F2 divided by K negative 1. And remember, there is a square for fluorine, so we have to take the square root of this in order to have fluorine by itself, or just do a 1/2 power. So both of them will work. At the bottom, it's just more literal to what it is asking, relating the atomic fluorine concentration to the molecular fluorine concentration. But if your answer is the one in the red box, that totally works too. The experimental rate law for the decomposition of ozone is second order in ozone and inverse first order in molecular oxygen. The overall rate reaction is over here. Show that the following mechanism is consistent with the experimental rate law, which is this one. and relate the observed rate constant K to the rate constants for the elementary reaction. So that means that we are going to try to express K using the K1, K-1, K2 that is down here. So that's start. So first thing, in order to show that the mechanism proposed is okay, first of all, the thing that we can see is that the elementary steps that just say this is step 1 and step 2 can add up to become the overall rate reaction, which it is obviously the case. And then the second thing we have to do is to determine the rate law of each elementary reaction. So this is K1, K-1, and K2. I am unable to type it in because of technology limitation, something along that line. So over here we can see that the rate law is O3 K1 and then K-1, these two. So the rate law for the first one is going to be K1 multiplied by O3 to the first power, because we can imagine that the stoichiometry is 1. Again, the reason why we can use the coefficient right now is because the rate law that we are trying to express is it's relative for the products and reactants. So we can see that we are setting the products and the reactants to be on the same equation, and that's why we can use the coefficients, so the one that was not there. When we're doing integrated and initial rate laws, we don't have this relative relation, and that's why we couldn't use it. And this is equal to the rate. So that's the first one. We can see that the reactants and the products. And for this is reaction 1 and this is reaction 2. For the second reaction, we can see that there is no inverse reaction, so it's not at equilibrium. So it's just K2 multiplied by the concentration of O multiplied by the concentration of ozone is equal to the rate. And the reason why we don't have a inverse one like the top one is because it is only a forward reaction. So it is only dependent on the reactant. So this reactant. Whenever we have a double arrow, that means we're at equilibrium, so the reaction can go this way or that way. So both of them can act as a reactant, essentially. And that's why we have to do them both. But that is determine the rate law for each elementary step. And then the next thing we have to do is to determine the intermediates. So recall that our overall reaction looks like this. So anything that is not O2 and O3 is an intermediate. That means that the intermediate is going to be O, so molecular oxygen. And number 3 is to reorder the rate laws in terms of the intermediate. So before we do that, we have to make sure that check number 4, it says to rewrite the rate law of the rate determined step. Out of the step 1 and step 2, the rate determined step is the slowest one, so it's the second one. So our rate determined step is this one, and this is the rate law. And we can see that inside the rate law, we have 2 concentrations. One of them, O3, is part of the overall reaction, so it's a concentration that we can track. But O, the molecular O, is an intermediate, so its concentration we cannot track, and that's why we have to try to express it using in an alternative way. So we have to take a look at reaction 1 and see how we can express this in terms of O. So basically we're going to rearrange this one and say that O is equal to something. So all we have to do is divide this part. So divide this part by the one in the box. So K1 multiplied by concentration of O3 is K-1, and then concentration of O2 as well. So that will be how we can rearrange the equation to express it in terms of concentration of O. And with this information, we can then replace this part with the O that is down here, because the concentration of the intermediate cannot be in the final version. So that will be K2 multiplied by K1 times O3 divided by K-1 times O2. Remember that we still have an O3 on the outside. So the O3 is still here. All we did is replace the O, which is just this part. So we have to clean this up a little, and then we can see that over here, after we clean it up, we have K2 multiplied by K1 divided by K-1. So these are all the K's multiplied by O3 square because there is 103 and 203. So multiply by each other, that is squaring, divided by O2. So comparing this with the experimental rate law that we found, which is in the question, and I'm going to write it here. So the experimental rate law that they found over here, we can see that it is consistent because these two parts correspond. This is this. And then the K, the experimental K that we get, so this is the thing that was determined by experiment, is consist of these three terms from the elementary step. So it is asking us to relate the observed rate constant K, this one, to the rate constants for the elementary reactions, which are these. So that step is essentially asking us to say K, the experimental one, is equal to K2 multiplied by K1 divided by K-1. So that is relating the two rate constants. Remember, this one is the experiment one, and these are from the elementary steps, which is something that we predict, and that can show us its dependence on the forward and backward reaction. And in this reaction, this example is a little bit more complicated. It is going to involve a little bit more steps. And again, I hope that you can attempt it yourself, and we are going to go over it in the video as well. Nitrile chloride, NO2Cl, decomposes to nitrogen dioxide and chlorine gas according to the following mechanism. And there are three elementary steps down here. Determine the overall reaction, write the rate law expression for each elementary reaction and identify the intermediates, then determine the overall rate law expression. So there are three things that we need to do. First is to determine the overall reaction, and then we can write the rate law expression, identify the intermediates, and determine the overall rate law expression. So before we do anything, just by looking at this, we can determine the overall reaction because all we have to do is to add all the elementary steps together. So basically add everything on the left side together and add everything on the right side together. So let's try that. So that is 2NO2Cl gas plus N2O gas plus Cl2 gas plus NOCl plus ClO. Okay, so what I just did is these are the reactants, and this is going to become what are the products over here. So these. So the products are going to be ClO2 gas plus N2O gas plus ClO gas plus NO2 gas plus NOCl gas plus NO2 plus Cl2. Okay, so now we have the reactants and also the products. And the next thing we have to do is to clean it up, essentially cross out whatever is the same before and after. So ClO2 gas, it occurs twice. N2O gas, it happens. ClO, it happens too. NOCl, it is also at the reactant and the product. And remember that the ones I crossed out are the ones that is in the reactant and also in the product. So now I say that out loud. Let me redo the part so that way you can see the colors crossing out, and hopefully that makes it a little bit more clear. So NO2, NO2, ClO2, ClO2, NOCl, NOCl, and ClO, ClO. So the overall reaction is us writing down what is left after we cross everything out. So it is 2NO2Cl gas becoming NO2 gas, and there is two of them, so 2NO2 gas plus Cl2, and that will be the overall reaction. So that answers the first question over here. And in order to determine the rate law expression of each elementary reaction, we'll just do them one by one. So I am going to note the K1, K-1 as it was described in the previous text. So remember that the way how we can note the reaction is doing the K1 is associated with NOCl to the second power. So it is going to be K1 times NO2Cl to the second power, and the 2 comes from here, is equal to everything on the right side using K1, K inverse multiplied by ClO2, and it has a coefficient of 1, so to the first power multiplied by N2O to the first power as well, and multiplied by ClO to the first power. And this part came from using these three and the K inverse one. So that is the rate law for the bottom one. So remember, I think the one that is important to note is that where the 2 comes from. So the power does matter. And we'll do the same thing for the ones at the bottom. So it's going to be K2 N2O to the first power. So I'm going to not write them. And then like that. So that is the reactant side using K2. And the product side, we're going to be using K-2. So K-2 indicating that it is the inverse reaction of the second one, multiplied by NO2 to the first power and NOCl to the first power. And again, the power is dependent on the coefficient. And the last one, we're going to do the same thing, K3 NOCl and ClO. Again, the reason why we know the power is because, and the reason why we can use the power as the coefficient of the balanced chemical reaction is because right now we're setting the left side to the equal to the right side. So basically the rates in this case, they're relative to each other, and that's why we can use the coefficient. While previously, when we were doing the initial and integrated rate law, we did not set the right side to equal to the left side, if that makes sense. And that's why we couldn't use the coefficients, because the coefficients are relative to each other. So again, your equation has to be balanced in order for this to work. But this again comes from the right side, and that is just going to equal to the rate. So if you want to add rate equals, and that is the rate law for each elementary step. So from here, we can again determine the intermediates. So the intermediates are the ones that is not involved in the reaction. So from the overall reaction that we wrote previously, the ones that we cross out because they are not in the final reaction. So you can refer back to the overall reaction that we just did and see which ones we crossed out. So the ones we crossed out include ClO2, N2O, ClO, and then NOCl. So these are the 4 intermediates that we crossed out. And we are going to be needing to know this intermediate in order to move forward. The third step for this reaction is to basically try our best to reorder the rate laws in terms of the intermediates. when we're looking at the intermediates, before we start doing that, let's look at the fourth step. We have to rewrite the rate law of the rate determined step. So in this case, the rate determined step is C, which is the slow one. So that means that the one that we are trying to rewrite is C. So the rate equals to K3 multiplied by NOCL multiplied by CLO. This is the one that we're trying to rewrite. That means that we have to replace the one that has an intermediate, because remember, the concentration for the intermediates are the hardest to track. So we have to replace the concentration of the intermediates by something that is in the overall rate, something that we can track. So the intermediates that we have to try to find a way to reorder is NOCl as well as CLO. So these two are the intermediates that is in the K3, the rate determined step reaction. That's why our goal is basically to try to figure out how we can rewrite these two out of the four intermediates that we have. So with that set as our goal, let's look at the first two, because we're using the third one as a rate determined step. So when we're rearranging the reaction, the only option we have is the first two. So the first one is K1NO2Cl2, and then K minus 1. Remember that all these K's, they're going to be lowercase k. It's just that my bad handwriting is making them look a little bit ambiguous. So in this case, for A, let's try to express the CLO. So for the CLO, and that is the reason why it should be CLO is because there's no NOCO in here. So CLO is going to equals to everything on this divided over this. So everything on the left side divided by everything in the circle, if that makes sense. So I'm going to start writing that. So that is K1 multiplied by NO2Cl to the second power divided by K negative 1 multiplied by ClO2 times N2O. And for part B, this is our original one, K2 N2O, and then ClO2. So I'm just writing down what we found in the previous step because I couldn't get them to be on the same page. So we are trying to express NOCl in terms of everyone else. So that is going to be NOCl is equal to basically everything here divided by this. So that is going to be K2 N2O ClO2 divided by K negative 2 and then NO2. So that is how we rewrite it. And now after we have those, we can now put them in there to identify the overall rate law expression. So over here, what we're going to do is put this into CLO, put those into NOCl. And let's start writing. So it's equal to K3 multiplied by K2 N2O and then ClO2 divided by K negative 2 NO2 and then multiply by the ClO1, which come from the top one, K1 multiplied by NO2Cl and then K negative 1 multiplied by ClO2 and N2O. Okay, so now we have finished it and we just have to clean it up so that it looks less complicated. So we can see that the N2O from here and the N2O from there can cancel out because they're all multiplying by each other. And then the ClO2 and the ClO2 can cancel out. And that will be about it. And you can see that what is left is actually the ones in the overall rate equation, right? The overall rate expression, the overall reaction, the one that we did at the very beginning contains NO2Cl, which is a concentration that we can track, and also NO2 is also a concentration that we can track. So the reason why we have to try our best to express the intermediates and then go through all this step is because in the rate determined step, we have to have a measurable concentration. But the intermediate concentrations are so hard to track because the intermediates basically they come and then go. While as the ones in the overall reaction, we know the initial and then we know the final because we know they're there all the time. They are the final products and reactants that will be there. While the intermediate, they're literally just a middle step. So all we have left is to rewrite this whole thing. So let's rewrite this. So we have K3 multiplied by K2 multiplied by K1 divided by K negative 2 multiplied by K negative 1. So this is all the K's that we have. And then we have NOCl2, NO2Cl divided by the NO2. And this NO2Cl is to the second power. And remember that the reason why we have a over the concentration because we have an inverse dependence on the product because the product is of the one of the equilibrium ones. So because they're in equilibrium, that's why we have a weird inverse dependence on the product, which is relatively unusual, but it's all because of being in the equilibrium. And this will be the final answer that we are looking for the overall rate law expression down here at the bottom. So again, it was a long process, but basically the first thing we do is to determine the overall rate equation by adding everything up. And then we write the rate law for the individual ones. Third one, we then determine the intermediates by looking at who was crossed out when we were finding the overall equation. And for the third step, we basically reorder the rate laws that we determined in terms of the intermediate because we're trying to use them to replace the overall rate law. And therefore, what we did is we look at the rate law, which is from the rate determining step C, and then see which intermediates we have to replace. And then we go back to say, okay, we need to find a way to replace NOCl, also ClO, and that's why we did all the rearrangement stuff. After we find that, we plug it in, cancel it out, and find our overall one.